the bottom of your screen, and we'll go ahead with that.
All right, let me go ahead and where's that? Oh, it switched over there. Okay. Yeah, I'm gonna give you what now I realized it's a very basic uncertainty quantification problem, but at the time was a complete revelation for me in the way that uncertainty could be quantified. And so the novelness in this, I think, is more the application and the cool place where I got to use it, more so than the methods. But let's just dive into it. So I'm Ravin Kumar. I'm very Bayesian these days. I very much enjoy uncertainty quantification with many packages, but I happen to contribute to these two. And I, in particular, enjoy doing applied uncertainty quantification in industry. As mentioned, I am a Bayesian practitioner. So in addition to Google, where I'm at now, I worked at SpaceX for a time, and then in the U.S. there is this restaurant chain called Sweetgreen, which also had a number of problems, where uncertainty quantification was quite applicable and quite helpful. But I'm going to focus on rockets. I think a lot of people are fascinated by rockets, as am I. And I want to talk about math. So I came into uncertainty quantification not knowing that I needed it, but more so just that I thought mathematics was awesome and it could build fantastic things. So my traditional degree is in mechanical engineering, and I learned a lot of mathematics that looked like this. No, in this equation, we don't have any uncertainty. This is just a rocket equation of what it takes to get a certain amount of mass to orbit. And then this is more math that once you get to orbit, how far you have to be with enough velocity not to fall back into the Earth. So I thought it was just very cool that you could use mathematics to describe so many different phenomena in the world and, frankly, just the entire world around us. The challenge I had, though, is that building rockets and the mathematics behind it was much different than the mathematics of orbit. So orbit is defined by the laws of physics. The equations fall out quite beautifully in a number of ways where you get specific velocities. But building rockets and building a factory, there's no rules of laws of physics that apply to the lead times and the processes and the organizational mechanics that go into building rockets themselves. So this isn't a hypothetical question because at SpaceX we were building many rockets. So the question became, how long would it take to build each one of these rockets? So to motivate this more and give you some more intuition behind this problem, I don't think anybody thinks that a rocket just appears out of nowhere, but usually rockets, or actually all rockets, need to be built in a series of pieces. You can think of it like a Lego, but many more millions of pieces that are quite expensive. So we're just going to focus on the two biggest pieces, which was the second stage and the first stage. These are two components here, and then you need to put them together, and that ends up building an entire vehicle. The challenge is you don't actually know how long it takes to build any one of those SpaceX rockets. There's ideas a priori, maybe we put in the system it takes 4 days to do this and 5 days to do this, which means that this block will be 5 days, and then maybe the final build takes about 10 days, so this will take 15 days. Everyone's got point estimates and point numbers, but in reality, we don't. For the rockets moving forward, it's not always going to be exactly 15 days. So being people that like uncertainty quantification, or in my case, where I was at the time, is I just had some data, and this was the data that I had. This is the first stage, the bottom portion of the rocket, and the data I had was I had a 1, I had a 3, I had a couple 3s, and then I had a bunch of 4 days. So 1 day, 3 day, 4 days. And the question I was going to ask is, how long is it going to take to build the very next second stage? So not this one, not the ones that have already been built, because we already know they've been observed, but the one right after. The thing that everybody does easy is like, why not just take the mean, and it ends up being right here. So we'll just say like 3.2 days or whatever it may be. That certainly works. That's one central tendency measure, but it begs the question, right? Like it's not like the next rocket is. It's very unlikely the next rocket is going to take exactly 3.2 days to build, or the first stage is going to take 3.2 days to build. And And it's not like the one after that is also going to take exactly 3.2 days to build. Like clearly there is some level of uncertainty in this problem, but we're losing all of that by just taking the mean. So the next thing was coming from mechanical engineering was, why don't I just use a frequentious analysis, which was try and fit a normal distribution somehow to this. The challenge I was having there is that I wasn't necessarily hypothesis testing these whether one rocket part was taking significantly longer than another, and that's the framework that I had learned in college. And at the time, I thought that's what all statistics was. But this is what I needed to actually get from the problem, not a hypothesis test. It was, I want to use all the available data. I would like to incorporate some expert knowledge. We'll talk about that in a second. I wanted to scale this to a ton of parts, and I wanted to easily be able to share these results with colleagues. And so if we talk about math again, this is where I finally learned about Bayes' theorem. And so I'm sure you've seen the math many times. There's a likelihood, there's a prior, and there's a posterior. The versions I had seen had done a lot of were point estimates in the past, and they had the marginal likelihood at the bottom, and they were about like coin flips or Monty Hall's problems. So I didn't initially recognize that there was a different way to use Bayes' theorem. And so there was a way to build Bayes' theorem that isn't just plugging in point probabilities, but it's much more of a workflow, which is taking things from what we know beforehand, which is the prior. What distribution do we expect to reasonably fit the data, which would be the likelihood, and then any constraints. So you could do constrained likelihoods and things like that. There was a way to not just plug point numbers into here, like 0.6, 0.7, whatever, but think more holistically and represent that in mathematics. And so this is what that looks like in code. So this is a pymc model, and I have all those components there. I have a prior for the mean and the standard deviation. I have a lead time, which is modeled by a truncated normal, and it let me get here. Well, actually, just let me get started. So let me first sample the prior and see that this is what, before we incorporate the data, what we think this would be. The prior was helpful because another challenge with the mean was there's a lot of people at the company that have expertise in building rockets, and they would bristle if I just came to them with a number and said this is the number and that's it, and there's nothing else. That's the pure mathematics. By having a prior, it gave me a way to work with others and understand where beliefs were coming into a problem. With a prior, you end up with a bunch of samples. So this is actually the samples for the prior predictive. Samples were helpful because then I could go in and not just have one number, but have again the distribution of the different values that possibly could have happened. Again, prior to incorporating information. And what pymc made it quite easy was it also made it easy to then get that posterior. So I won't go into the details here unless somebody would like me to, but pymc at the time, and still today, makes it so you don't have to think about the mathematics of computing a posterior. This is also like Stan or NumPy or other PPLs. I could just express my problem, I could hit run, and then I would get a bunch of samples. So just one more line of code, and now I have a lot of posterior samples. And here we had it. I had posterior distributions of parameters. So I had the mean of the distribution and the standard deviation of our truncated normal. In this case, though, I didn't care about the model parameters. What I really cared about was the posterior predictive, because the posterior predictive is what tells me what is it likely going to take for the next rocket and the one after that and the one after that. Sorry, and I should say first stage, the next first stage, the one after that, and the one after that. And so I'm sure folks here have seen the Bayesian update, but this is what it looks like in action. The prior may say something like this based off of prior beliefs, and then with the Bayesian update, we get some updated posterior beliefs. So that gets us one of these, the first stage. But the cool part is then I could repeat these for the second stage and the final build. And so I could just run this process over and over again, and I would end up with 3 distributions. And then the cool part was I then could Monte Carlo sample from all these different posteriors, add them together, and I would get the full distribution of rocket lead times. And so then I could say, oh, likely that a full rocket from here to here is going to take anywhere between 5 and 20 days. And I could even say the number of samples between 5 and 10 is this much. So if we want a rocket to speed up and be faster, we want to bring down the samples that are above 20 days. This is how likely that outcome is, and do we need to intervene, like accelerate the process somehow by rearranging some work, paying folks extra for overtime, and really enable some business decisions that stemmed from end-to-end uncertainty quantification. So I just talked about this slide here, and this is what's called a bill of material, and this is one for what looks like a valve. And so the same idea that if you're going to build a pilot valve, there's all these different parts. These all take time. You can estimate the different lead times, add it together, and you end up with the total lead time for a pilot valve. And so why this worked in practice for me? Small data is what I had at SpaceX, and uncertainty quantification, especially with Bayes' theorem, works with small data, and so it was the only method that worked for me at the time. It's principled, so better than just guessing in a meeting room, which is what happens in the absence of that. Maintaining uncertainty was important, so I know this conference is all about uncertainty quantification, so I don't have to sell you on that. But the other parts were incorporating human expertise, which helped people buy into the solution in a language that people understand, which wasn't p-values or probabilities, but just plain days. It's going to take this many 5 days to 20 days. And then with pymc, it was quite scalable. And it's actually, I'm noticing the same thing with Bridge now 5 years later, right? With these toolings, it doesn't become an academic exercise to do uncertainty quantification. Tooling makes it quite easy to then scale these to large sets of problems. So I'll skip through these slides because I think you folks are quite familiar with Bayes, and this was part of. But in case you're not, there's, in addition to just simple distribution fitting, you can do regression with Bayes, Gaussian process fitting, change point detection, and many more. If you're interested in any of the slides, all the code for this is on GitHub, and I think I'll be able to share the slides somewhere. But if not, you can ping me and get them. But all the code's on GitHub. The book here is free. You can get that. I have a series of courses for folks that like package courses that I've written with my pymc fellow co-authors. And then lastly, the reason I get to speak at this conference was I actually got a submission from Linus and Anne for pymc-con a number of months back. So we have a running series on pymc and uncertainty quantification of pymc. They're slated to talk next month on Bridge, and Linus was like, well, how about I raise you on and you speak at my conference next week? I was like, okay, why not? So if you want to see more about Bridge, come to pymc-con, where I don't exactly know what Linus is planning, but you're gonna get more of this uncertainty quantification goodness, as with all the talks that already exist and many more to come. And so that's all I have. I'm happy to take any questions. I don't know how questions work in GatherTown, so if somebody has one, just